So hi all, welcome to the lecture series on solving previous year questions on GATE examinations related to analog circuits. So here today this is the part 1 of solving the questions related to BJT and MOSFET circuits. So let us see one by one. So this is the first question. So this is the first question, and this question is related to the BJT amplifier. So this question was taken from GATE 2025. So let us start. The question is: a simplified small signal equivalent circuit of a BJT based amplifier is given below. The small signal voltage gain V0 by Vs is equal to dash. So we have to find, so this is the circuit, we have to find the V0 by Vs, okay, the gain. So how to find this? So we'll see. So here if you see, it's a small signal equivalent of a BJT amplifier. If I correctly note, then this will be the base point, this will be the emitter point, and this will be the collector node of the amplifier. Okay, so the question is to solve V0 by Vs. So what is V0? V0 is the voltage at the output and Vs is the input voltage, right? So we'll solve this. So let me draw this here once more. So this is a circuit. Okay, so this is the Vs voltage. We'll select this plus minus, and this is V0. The voltage across R is the V0, and this is a current IB flowing in. Okay, this is a current IB. Okay, and this is actually, so this is actually a dependent source. So where it's a current source and the current depend upon the current IB. So we need to find V0 by Vs. Okay, V0 by Vs. So how to find that? So first we will find the voltage V0 in terms of IB. So here if we analyze here at the output, if we analyze at this output node, the voltage V0 is the voltage across this RL, right? So this is plus minus, and if we see there is a current source beta IB, it's a dependent current source, and the flow of current is in this direction, right? So this will be the current direction. It will flow from the ground into this source, right? So how the voltage drop across RL will be? It will be something like this, plus minus, right? So if I write V0 in terms of IB, it will be like V0 equal to, right, the current is flowing from bottom to top, so the voltage potentially is like here plus, here minus. Okay, so how V0 we can write? V0 is minus beta IB into RL. So this is the voltage V0. Fine. So here we need to find V0 by Vs. So what we have to do is like we have to find this IB in terms of Vs, right? So from the input network, if we see here, the voltage Vs is from the node, this node to the ground, okay, is Vs. So across this node and the ground, okay, across this node and the ground, there is two resistance, Rs and Rpi. So Vs is the voltage across this Rs and Rpi. Okay, so what will be the current flowing through this resistance Rs plus Rpi? That is the current IB. So from this circuit, it's clear that the current IB, okay, the current IB is equal to Vs by Rs plus R pi. Fine. So we can substitute. So this is the equation 1 and this is the equation 2. Okay. So we'll substitute equation 2 in 1. Okay. So what we will get? V naught will be equal to minus beta into IB is Vs by Rs plus R pi, that into the resistance here it is RL. So RL. Fine. So we can write, so I can bring this Vs to LHS, right? So it will be like Vs V naught by Vs equal to minus beta RL by Rs plus R pi. So this is the gain V naught by Vs. So if we see here in the options, given options, the right answer is option A. So that is the option. So answer of question 21, option A, minus beta RL by Rs plus R pi. Fine. Yeah. So now we'll see the second question. That is question 22 of GATE 2025 again. So we'll see the question. So the question is, the ideal BJT in the circuit given below is biased in the active region with a beta of 100. So given beta is equal to 100. Okay, and given if IB is equal to 10 microampere, when then VCE involves round off to 2 decimal places is okay. So the question is to find the voltage VCE. Okay, so this is the circuit, and if we carefully see here, here we have, this is the BJT, and we have 3 resistors, one 5K from the collector to VCC 10 volt, and there is a resistance RB connected from the collector node to the base. Okay, and from emitter to ground there is one resistor 3 kilo. Okay, and the question is to find the voltage across the collector and emitter node VC. So let us solve this. So I will draw this circuit once more. So let me draw here. Okay, this is RB, and the question is to find the voltage at this node, VCE. Okay, and we'll draw what all has been given. So here it is, current is IB, and given IB is equal to 10 microampere. Okay, and beta is equal to 100. Okay, and we will draw the other currents. So we know, so this is the collector node, right? So this current will be equal to IC. This current is IC, and this current is IE. So if you carefully see here, the current IB is like coming from this node, right? It is coming like this. So this is IB. So what is the current here? This current will be IB plus IC. Fine. So, and if you see here, this here we have applied 10 volt. So what is this? So at this node we have applied a voltage source like this. Okay, so this is the 10 volt. So minus plus. Fine. So if we annotate the potential or polarity of the potential across this resistance, if you see here, the current is flowing from top to bottom, right? So there will be a voltage drop like this, plus minus across 5K, and across the collector and emitter node we have VCE plus minus, and the current IE is flowing from emitter node to the ground. So there will be, so it is flowing like this, right? So there will be a voltage drop like this, plus minus. Okay, now I will apply the KVL, right? I will apply the KVL like this. So I'll apply KVL like this. Okay, so on applying KVL here, so what I will get, so from this node, if I take from the left hand node ground, I'll have minus 2 plus 10 volt, right? So it is like, oh sorry, I'm sorry, yeah, so it's 10 volt minus, right? So the other node is voltage across the 5k, so it is plus minus, so it will be 5k into IC plus IB, okay, minus VCE, voltage across the collector to emitter, minus the IE into 3k, that equal to 0. So net voltage is equal to 0, right? So this is 5k. Okay, so here we know we have IB equal to, right, we have IB is equal to 10 micro. Okay, and from here we can also find IC, right? So what is IC? So IC is beta IB, fine, and IE, what is IE? IE is beta plus 1 IB. So we know this relation between IC, IB and IE, fine. So substituting this here, so what will be change? So this will be equal to 10 minus 5k into IC is beta IB, right? So I can take IB outside, so beta 1 plus IB, beta plus 1 into IB, minus what is VCE given. So in the question VC we have to find, right? Sorry, VCE minus IE is beta plus 1 IB into 3k equal to 0, right? So it is 10 minus beta is 100, right? So it is like 5k into 101 into IB is 10 micro minus VCE minus this is again 101 into 10 micro into 3k equal to 0. So from here we can find what is VCE. VCE is 10 minus, so here it is like, so 101 into 10 micro, 101 into 10 micro is common, so it is like 8k into 101 into 10 micro. So if we solve this, the value will be equal to 1.92 volt, fine. So this is how we find the voltage VC. So it's very easy. So the question is, so answer is option C, 1.92 volt, fine. Yeah, I'll go for the next question asked in again GATE 2025, that is third question. Okay, so we'll see this. So question is the identical MOSFETs M1 and M2 in the circuit given below are ideal and biased in saturation region. M1 and M2 have a transconductance GM of 5 millisiemens. The input signals in volts are, so the input voltages they have given, V1 equal to 2.5 plus 0.01 sin omega t and V2 equal to 2.5 minus 0.01 sin omega t. The output volt signal V3 in volt is, the question is what is the voltage V3? So this is the circuit given here. It's a differential amplifier made of MOSFETs M1 and M2. So here we have the input voltage V1 and V2 and it is biased by a DC voltage source of 5 volt and there is a current source of 2 milliampere DC 2 milliampere, and both the loads are equal. See, 1 volt and 1 kilo ohm and 1 kilo, and given M1 and M2 are ideal and identical, right? So both, if we carefully see here, if I just cut this, both this part 1 and part 2 both are identical. Fine. So from this itself we can write one thing, that is the DC, though the DC voltage here is 2 milliampere, this 2 milliampere will be split across the two arms of part 1 and part 2 equally, right? So this current here and this current here, that is DC current. Okay, DC current will be 1 milli and 1 milli. So this will be DC current. Okay, DC current will be equal to 1 milli, it will be split equally, right? And this 1 milli will come through this part and this part. So 1 milli plus 1 milli will be equal to 2 milli. Fine. So that is there. Okay, and apart from that, the V1, if you see here, V1 is equal to 2.5 a DC volt plus 0.01 sine omega t. So this is a sinusoidal voltage, and V2 is equal to 2.5 minus 0.01 sine omega t. Okay, so here 2.5 and 2.5 is the common mode voltage, and 0.01 sine omega t and minus 0.01 sine omega t is the differential voltage, right? Yeah, so we'll see, we need to find here the voltage V3, that is voltage at this node of M1. Okay, so how to find this? So the voltage V3 will have two components. One is the V3 DC voltage, and there will be a component due to AC. Okay, so how to find the voltage V3 is like, we will find both DC and AC separately and we will add it. That will be easy. Okay, so from here, if we see what is V3 DC, okay, what is this voltage? The V3 DC voltage. Okay, so if we see here, we know the DC current flowing through M1 is 1 milliampere, right? So what will be the voltage here? So I will just draw here. So voltage, sorry, the MOSFET is M1, and there is, we need to find the voltage V3. Okay, and some current is flowing, so I am not drawing this. So we have applied some voltage V1, and there is some DC volt 5 volt applied here, and this is 1K. Fine. So we know for DC, whatever the input voltage, since we assume that it is in, so the question is given like it is in saturation, right? Yeah. So it is conducting. Okay, so if it's conducting, the DC current will be constant, right? So the DC current here is 1 milli. Okay, so if such a current is flowing, there will be a voltage drop plus minus here, and the rest voltage will be from this node to the ground. Okay, between this node will be V3. Okay, so this V3 is the DC voltage. Okay, so what is this V3 DC? That will be, what is the net voltage across from this node to the ground? That is 5 volt. Okay, so what will be V3 DC? That will be equal to 5 minus the voltage drop across this resistance. So that is 5 minus 1 milli into 1K. So that will be equal to 5 minus 1, that is equal to 4 volt. So definitely the DC voltage, V3 DC voltage will be 4. Okay, so if we come to this options, we can see 4 plus 0.1 sin omega t and 4 minus 0.05 sin omega t. So here we can say like either C or D will be the answer, because DC voltage is 4. Okay, we just need to find what will be the AC voltage now. Now coming to the AC, so V3 AC. Okay, so how to find V3 AC? So if we draw the small signal equivalent of this MOSFET, it will be like this, the pi model. Okay, so it will be GM VGS. Okay, this is the voltage. So if this is the node, gate node, this is the source terminal, and this will be the drain terminal. Fine. And this is this pi model. Okay, this is a pi model of a MOSFET. Okay, so here given at the gate it is V1, the voltage applied here is V1. Okay, and since it's a AC equivalent, we just need to draw the AC value. What is the AC value here? It is 0.01 sin omega t. So here it is 0.01 sin omega t. Okay, and so the source is connected to here to this node, that is source of the other MOSFET, and in AC analysis the 2 milliampere the DC current source will be open circuited, right? So we will say like this is connected to the second MOSFET. Okay, source of second MOSFET. So some current is flowing through this. Okay, now what is at drain? Okay, at drain it is like I have connected to a 1 kilo ohm to DC. So DC voltage source will be short circuited to ground, right? So we can write like I have a resistance like this connected to ground. So this resistance is 1K. Fine. And this node voltage is V3 AC. Okay. So from this figure, what is the current? So what is V3 here? V3 AC voltage, that is the voltage across this resistance 1K, right? So if you see here, what is the AC current flowing here? AC current flowing here is like this. So this is GM VGS. Okay, and this will drop a voltage like this, plus minus. Okay, so V3 AC will be equal to minus of this current, that is GM VGS into 1K. Fine. So minus GM into VGS. So if you what is VGS here? So given VGS is the voltage across the gate to source node. Okay, so what is this voltage? So this voltage is equal to this voltage, right? 0.01 sin omega t. So it is equal to minus GM VGS, sorry, not VGS. So this voltage is this into 0.01 sin omega t. So this is the VGS, that into 1K. Sorry. Okay, so here what is GM? So given GM is 5 Siemens, right? So this is equal to minus 5 is 5 millisiemens. So 5 milli into 0.01 sin omega t into 1K. So kilo and milli get cancelled off, and this will be equal to minus 0.05 sin omega t. Fine. So what is V3? So this is the AC voltage, V3 AC. So effectively the V3 will be equal to V3 DC plus V3 AC. So if I substitute it, V3 DC is 4 volt minus 0.05 sin omega t. So this is the AC voltage. So net V3 will be equal to this much. Okay, so in option it is option D. Okay, 4 minus 0.05 sin omega t. Okay, so that's how we solve this question. So that was the third question. Now we'll see the next question, fourth one. Let us see to the next question. So again, this is from GATE 2025. Okay, so it is a combination of this question is a combination of BJT and the Zener diode. Okay, regulator circuit. Okay, so we'll see here. Okay, so the question is, in the circuit shown below, the identical transistors Q1 and Q2, so here two transistors Q1 and Q2 are biased in the active region with beta equal to 120. So both the transistor Q1 and Q2 is identical with beta equal to 120. Okay, so given beta equal to 120 for both Q1 and Q2, the Zener diode is in breakdown region with Vz equal to 5 volt and Iz equal to 25 milliampere. Okay, if IL is 12 milliampere and VEB1 equal to VEB2 equal to 0.7 volt, then the values of R1 and R2 in kilo ohm are dash respectively. So we need to find the values of R1 and R2 in this circuit. Okay, and the question is like we have been given two transistors Q1 and Q2, both are PNP transistors and both are identical. Okay, so let us solve this. So if we carefully check here, so here the base of this transistor Q2 is connected to the collector, right? So this node and this node are same. Okay, so and here if you see here, VEB2 is a voltage from this node to this node, or we can say like from this point to this point is same as VEB2, and given VEB2 equal to 0.7 volt, right? It is 0.7. So I can say like here it is 0.7 volt. Okay, and the voltage across the Zener, right? The next node is from this node to this node. So that is the voltage across the Zener, and that is Vz. So this voltage is equal to plus minus, it is 5 volt. Okay, and from this node to ground we have the resistance R1. So we don't know what is the voltage across this R1, VR1. So if we carefully check in this circuit, the voltage across this point to this point, right, is 20 volt, and till this node this voltage is split as 5 volt and 0.5. So what will be VR1? So from the circuit, right, okay, from circuit we can say VR1 as 20, the net voltage 20 minus the voltage drop across this emitter and collector of Q2, that is 0.7, minus the voltage drop across the Zener diode Vz, that is 5, right? So this will be equal to 14.3 volt. Fine. So the question is to find R1. So what is R1? R1 is, right, the R1 will be equal to VR1, the voltage across this resistance R1 by the current through R1. I will call it as IR1. Okay, so if we see here, what is IR1? IR1 is the current at this node. If you see, if we apply KCL at this node, it will be like IR1 will be equal to, right, I will say, right, VR1 by IR1 will be equal to IZ, the current through the Zener diode, plus the base current IB. Okay, so what is IZ? IZ is given, IZ is 25 milliampere, while IB is not given, right? But if we carefully check here, it has been like here in the circuit it is given like IL is equal to 12 milliampere. And what is this IL? IL is the collector current, right? IL is same as the collector current of Q1. Fine. So what is IC? IC is equal to beta IB, or IB will be equal to IC by beta. So IC is 12 milliampere and beta is 120, right? So what is IB? IB will be equal to 0.1 milliampere. Fine. So if I substitute here, so VR1 by, so I will substitute VR1 as the voltage we have derived, right? So we have derived VR1 as 14.3 volt, and given IZ is 25 milliampere, plus the IB is 0.1 milliampere. Okay, so it is like 14.3 by 25.1. So if we solve this, okay, sorry, so if we solve this, this will be equal to 0.569, okay, or approximately equal to 0.6. So this will be the R1. Okay, so this is R1. Similarly, we need to find the voltage across, the value of R2. Okay, so R1 is we have derived, we need to find R2. Okay, so here if you see for R2, if we see, we need to find the voltage across R2 and we will divide the current through R2, right? So the current through R2 is IE, right? So the current through R2 is the IE, okay? And what is the voltage across R2? So if we see here from this node to the ground is again 20 volt, right? So if you see this path here, this node I have the voltage as VR1, okay? From ground to this node is VR1, and from this node, that is this node to the emitter node, that is VEB1, that is 0.7, right? So I can say, right, at this node it will be like from this node to the ground, okay, to the ground it is like 0.7, that is voltage across the VEB1 plus the voltage VR1, okay? So that is the voltage. So I can say, so maybe it may be confusing. So this is the ground. Okay, so this voltage is equal to 0.7 plus VR1. Okay, how I find that? That is voltage across this two node and the voltage across this point to this point. Okay, so this is 0.7 plus the voltage across the resistance R1, that is VR1. So that is 0.7 plus VR1. So this is the voltage. And if I add the voltage across R2, that is voltage across this, I will get the 20 volt, right? So what is VR2? So from circuit, VR2 will be equal to the net voltage 20 minus the voltage at this emitter node, right? So it will be like 0.7 plus VR1, that is the voltage VR2. Right, so this will be equal to 20 minus 0.7 plus VR1 is 14.3. So 20 minus 15, that equal to 5 volt. So that is VR2. Okay, and what is the current IE here? Okay, so this is VR2. So what is the resistance? R2. R2 is equal to VR2 by the current through the resistance R2, that is IE. So VR2 by what is IE? IE is beta plus 1 IB, or in a simple way we can say like it is equal to IC plus IB. Okay, so VR2 is 5, and what is IC? IC is equal to the current IL, that is 12 milliampere. Okay, IC is 12 milli plus IB is, how much is IB? 0.1 milli, right? 0.1 milli. So this is like 5 by 12.1 milli. So this is approximately equal to 0.413 kilo. So this was kilo, right? Okay, this is kilo ohm. Okay, sorry. So I will say like this is approximately equal to 0.4 kilo R2. Fine. So the answer is D. Okay. No, sorry, not D. I'm sorry. The answer is A. Okay, 0.6 plus 0.4 kilo. So here the answer is in kilo. Okay. So this is how we solve this question. Okay. So let us go to the next question. That is fifth question. Okay, so this fifth question is from GATE 2024. So we'll see the question. In the circuit below, assume that the long channel NMOS transistor is biased in saturation. So the transistor is in saturation region. The small signal transconductance of the transistor is GM, and neglect the body effect, channel length modulation, and intrinsic device capacitances. Okay. So the small signal input impedance Zin of j omega is equal to what? Okay, so given the question is like this, and this is the MOSFET. So NMOSFET, and given it is in saturation region. Question is to find the Zin. So let me redraw this circuit here by redrawing the NMOS in its small signal equivalent. Okay, so how will I draw that? So I have the gate, drain. So this gate, this drain, and this is the source. Okay, so between gate and drain it is like open, and between the drain and source there is a current source, that is GM VGS. VGS the voltage across gate and source. Okay, and if you see here, this is the drain, right? Drain, this is the gate, and this is the source. So from drain it is connected to ground. Okay, and from source, now we will draw the circuit. So here at gate, okay, between the gate and the source there is a capacitance C1. Okay, so what is the impedance of this capacitance? I will write it as like 1 by j omega C1. That will be the impedance, right? ZC1 will be equal to 1 by j omega C1, and ZCL will be equal to 1 by j omega CL. That is the impedance of C1 and CL. Okay, and here from the circuit, from the source end, I have a capacitance to the ground, that is equal to 1 by j omega CL. Okay, so how to find the input impedance? The simple method is, okay, at this input, okay, I will apply a voltage V in, and the circuit will draw a current I in. So I will say like I in of j omega, V in of j omega, and what will be the Z in of j omega then? Z in of j omega will be equal to the voltage applied, V in of j omega by I in of j omega. So this will be the impedance. So this is how we find the impedance. Okay, so we will see here. So from the circuit, first we will see what is VGS. Okay, so VGS is the voltage across the gate and source, or gate and this node will say. Okay, and here the I in is the current flowing inside, and this current will be 0, right? So the current here, this will be equal to I in itself. Okay, and due to this current there will be a voltage drop across this capacitance, and this voltage will be same as VGS, right? This node is connected to gate, and this node is connected to source. So we can say VGS, right, from circuit we can write VGS as I in j omega, I in of j omega into the impedance of the capacitor, that is 1 by j omega C1. Fine? Yeah, so that is VGS. Now okay, now the question is to find V in by I in of j omega, right? So what is V in? V in is a voltage across this node to ground. So I need to find V in by I in of j omega in terms of the capacitors and the transconductance here. Okay, so in terms of the C1 and CL, what is V in? So V in is the voltage across the capacitor C1 plus the voltage across the CL from the circuit. So definitely there will be a current flowing like this, right? So there will be a voltage drop like this. So the voltage across C1 plus voltage across CL will be V in. Okay, so V in equal to, so I will draw right here. So from circuit, okay, V in of j omega will be equal to, one is voltage across the C1. Okay, so I will say like VC1 plus voltage across the CL. So what is VC1, voltage across C1? That is the current I in of j omega, that into 1 by j omega C1, that is the voltage VGS, right? Plus what is voltage across CL. So what is voltage across CL? The current through CL into the impedance of CL, right? So what is the current? Here we have, through this node we have the current I in, and there is also some current flowing from up, right, like this. So what is this current? This is equal to Gm VGS. So what is this current? That will be equal to I in plus Gm VGS, the voltage flowing across the current impedance CL. So I can write like I in voltage across CL as I in plus Gm VGS into 1 by j omega CL. Fine. So let us substitute the voltage VGS from equation 1. So it will be like I in into, sorry, I in of j omega into 1 by j omega C1 plus I in of j omega plus Gm into VGS is 1 by, sorry, I in of j omega by j omega C1 from equation 1, that into 1 by j omega CL. Okay. So if I take I in outside, it will be like here, oh sorry, Gm into 1 by j omega C1 into 1 by j omega CL, right. So this will be equal to 1 by j omega C1 plus 1 by j omega CL plus Gm by j into j is minus 1. So I will write as minus Gm, and this is omega C1 into omega CL. It will be omega square C1 into CL. So from this equation I can find the Z in as V in by I in, right. That is 1 by, sorry, not 1 whole divided by, can write as 1 by j omega C1 plus 1 by j omega C2 minus Gm by omega square C1 CL. Fine. So we'll see. So option A is the answer. Okay. Yeah. So that's all for today. The rest gate questions we will solve in the next part of the lecture series. So thank you all.